Welcome back to another video in CSC 263, Database Management Systems at Adelphi University. In the previous video I introduced some basic terminology about databases. Specifically, we talked about the difference between the terms data, database, database management system, and database application. Today we'll look a little bit in more detail as to how does the database management system and the database fit in its environment. This is chapter 2 in the book. So one of the major benefits that I briefly mentioned in the first video was that database management systems, and in particular relational database management systems, are often self-describing. That means that they maintain metadata about the data separately. Metadata is data about the data. So for example, I might maintain information that says, well, if I'm describing a person, I'm going to record a last name of the person and a first name of the person without necessarily immediately specifying what that name is. Because we have that metadata, it now allows us to reason abstractly about data. So we can talk about data in terms of its metadata. Gets a little confusing, all the datas and the metas and all of that stuff together, but stick with me for a second. The whole point is that we allow ourselves to take different levels of abstraction. The benefit of that is that we can eliminate elements that we don't need to think about right now. We're reducing the scope of our problem, and anytime that a problem becomes smaller, solving the problem becomes easier. Sure, later on we'll have to put all the pieces back together, but that's often not as difficult as it sounds, especially if you keep that in mind from the beginning. The ability to rapidly change different levels of abstraction and be aware that you're consistent on each level is one of the most critical skills that you'll develop as a computer scientist, or really as a person in general. One attempt to do this is to look at the ANSI-SPARC model. Now, this is not the end-all be-all model, but it is a model that is very often referenced, and again, probably because of its simplicity. Let's talk through this model from the bottom up. On the bottom, the ANSI-SPARC model talks about the physical layer, the physical data organization. So that talks about where is my data located? Is it located on a disk? What kind of disk is it? Is it a solid state disk or is it a physical disk? What kind of file system is created in that disk? Is it NTFS? Is it X2? Whatever it may be. Those are things that we don't want to have to worry about when we're developing database applications, and this model lets us do that. So in this course, for example, we are going to completely ignore the fact that data actually has to go somewhere. We'll make magic happen, and when we want to store data, poof, there is something that is going to remember the data for us. That is called the physical data organization layer, or just a physical layer. One layer on top of that is the internal level, and that is the level that is specific to the database management system. As the data application, you'll never interact with it. The database management system will take care of you. In the internal level of the database management system, we figure out where, for example, on disk we maintain these the data and what files. What are those files called? What kind of indexes do we need to create in those files? And what type of indexing algorithms do we use? How do we create journals and log files? And all of those things that make the DBMS work are happening on the internal level. So basically it's the guts of the DBMS happens at the internal level. If we are designing applications that use a DBMS, we also do not care about the internal level. Sometimes it is useful to know a little bit about it, but under most circumstances you can almost ignore the fact that there is such a thing as a database internals, because the DBMS will take care of that for you. Towards the end of this course, we'll dip a little bit into the internals, just to give you a little bit of a feeling for it. In this course, we will be spending the vast majority of our time on the conceptual level. The conceptual level, and there's only one of those, is where the database metadata is described as a whole. That is where we define in relational databases tables and keys and relationships, maybe even usernames and passwords. It is the comprehensive view of all the data in the database accessible through the database management system. There's only one conceptual level for our database, and all the data is described in it. The structure of the data, the nature of the data, how I access it, everything. Then we have the external level, and the external level is how we make the data appear to the database applications. So for example, I might be writing an application that should be able to pull up the transcript of a student. That means that I need to have the student's name, their ID number, the courses they took, and their grades. What I do not need, for example, if I'm looking at the transcript, is future course registrations, social security numbers, medical history, employment record, all of those things that might also be part of the database that I simply do not need. That is then determined through a view on the external level. The external level is also the level that your database application interacts with. So you don't talk directly to the conceptual level through the database application, you talk to an abstraction level higher. For example, in my database, I might store your date of birth, but I might present that at the external level as an age. The data is still the data, it's still the same thing in the conceptual level, but in this particular external view, I'm presenting your date of birth as an age, not necessarily as your actual date of birth. Maybe I'm developing an application for a bar, and I don't even care about how old you are. I just want to know that you're 21 years or older, and in that case, that might be how I present your date of birth, as a Boolean field, yes or no. All of those translations that are specific to an application, or sometimes maybe even to a user in an application, are called views, and those happen at the external level. As you can see in the diagram here, even though there is only one conceptual level and only one internal level, there could be many views, many external descriptions of the data. And that is by design, so that we can have different views of the data optimized for different stakeholders. That's the ANSI-SPARC model. Primarily the three top layers, the external level, the conceptual level, and the internal level. And what we have to realize when we are dealing with application development is at which three of these levels we're operating. Are we typically working at the conceptual level when we're talking about the database schema and the data? Are we using looking at the external level where we use the data? Or do we worry about the internal level, which specifies how the database management system organizes that data internally? Shortcut to remember: external level describes how users view the data in the database, not necessarily how it is stored there. The conceptual level describes what data is stored in the database and how that data is organized. That's primarily where we'll be spending a lot of our time in this class. The conceptual level is technology agnostic, so we don't necessarily know what database management system or relational database management system we're using when we're defining our conceptual schema, even though there might be some peculiarities for different products. In this class, we'll stick to standard SQL and standard relational database terms, where it doesn't matter whether you're on Microsoft SQL Server, on Postgres, on MySQL, whether you're on Oracle databases or whatever there may be out there. We do product agnostic, which also means that we will not talk about product specific optimization. So even though the solutions that we're presenting in this class might work, they might not always be the best solution for the given product that you have. It's give and take. If you start using those product specific extensions, you'll basically be saying that you cannot move away from this database ever again. Again, trade-offs to make. At the internal level, we figure out how data is stored, and at the physical level, how the OS uses its peripherals to keep track of the data. Now, we'll talk about database languages more, but for now we'll just give you a quick preview. Because we separate data from metadata, we're going to also introduce two variations of our database languages. One variation deals with the metadata, one deals with the data itself. The language part that deals with metadata is called the data definition language. The language that is focusing on manipulating the data itself is called the data manipulation language. These languages are different than what you have seen so far. At this point, at Adelphi at least, you have seen Python and you have seen Java. And both of those languages have in common that you specify to the computer exactly how to solve the problem that you want to solve. That is called a procedural language. You describe the procedure that you use to transform input to output. Typical database languages are non-procedural languages. They describe the desired output that you're looking for, given the input that you are presenting, and then the database management system gets to figure out how to do this. And so it means that you are relinquishing some control over how the DBMS obtains this data for you. That's okay though. It will take some getting used to, but we'll make that work. The language that we will be using is called SQL or SQL if you prefer that, and it's the same thing. It's the structured query language, and we'll talk about that a little bit in the near future. Like we separate the data from the metadata is called the data model. The data model is, and the definition is right there, is an integrated collection of concepts for describing and manipulating data, relationships between data, and constraints on that data. That sounds very abstract. It's we'll get to that when we get to that. It is important to know what modeling paradigm we use. In this class, we will focus on relational databases. So as we start figuring out what data we want to store in our database, we have to then translate or express what that data looks like in the terms of relational databases. There are other database paradigms, but we kind of glance over them. We briefly mention them, but we don't spend a whole lot of time on them. We have a graduate course on databases, and that focuses on everything except SQL databases. So that goes into more detail about different database paradigms. But briefly mentioning record-based. So the relational data model is based on math, but we'll glance over most of that. But the data is represented as tables, or as relations if you want to call them that. It's still by far the most commonly used database paradigm. We're starting to see more NoSQL data, for example, but not nearly as widely accepted yet as relational databases. Other approaches, the network data model, where we look at collections of records and how they are interlinked. Hierarchical data, where we talk about everything in terms of a big tree, all different ways to organize data. For now, focus on relational data for this course. Once we then start figuring out what our DBMS must do, we can see that it must provide a number of services. I already mentioned several of those in the previous video. But we want to be able to get to our data. That's the primary function of the DBMS. But we also want to make sure that we have transaction support, and we'll talk about that in the future when we talk about internals, what a transaction really is, what properties transactions need to have, etc., etc. We need to be able to do concurrency control. What that means is if multiple people are accessing the same data at the same time, we need to have some mechanism in place that they are not stepping on each other, where, for example, the second person may undo the changes that the first person made. We want to make sure that that doesn't happen. We promised that our database would provide persistence, which means that if something crashes or fails, we need to be able to recover. That's part of the function of the DBMS as well. We want to make sure that if we have multiple people interacting with our database, that those people are properly authorized. We want to make sure that they can do so over a network through data communication. We want to make sure that the data that goes in the database is as accurate as we can make it. And we'll talk about data integrity a whole lot more over the next couple of weeks. We want to be data independent. In other words, I don't want to have to worry about how to store stuff on disk. I just want to be able to use it and not have to know, if something is stored as a linked list in a C compatible file, for example. And I want to have some utilities in there, and we'll be using one of the utilities called the monitor fairly extensively. All of these functions must be present in a database management system before it becomes functional. That is the content of chapter 2 in the book. In the next chapter, chapter 3, we'll talk a little bit about the database architectures and the web. How does this fit in? We already know that a database or a database management system happens in the back end almost to a system. It's not a front end system by far, but how does that fit into the World Wide Web? That's the topic of our next video.